All right. Hello, everyone. Thanks for tuning in to today's Corundum developer meeting. So let me go ahead and get started with these slides. For the agenda, we got, as usual, announcements, project ideas, and then some status updates. So let's get into it. The announcements, the next Corundum developer meeting will be on November 20th in 2 weeks, and the next Switch developer meeting will be on November 13th. And again, I think both of these are at now 5 o'clock p.m. UTC or 1700 UTC because of the daylight savings time change in the US. So it may have resolved itself with several other countries that are also now on, a similar daylight savings time. But, be aware to check the time before joining. And as usual, I have been announcing on the Zulip channel right before the meeting starts, just so people know. If you're connected to that anyway. All right. So project ideas. I'm not going to go into this in great detail, but happy to talk about this more in depth if any of these look interesting. If somebody wants to sink their teeth into a somewhat self-contained project idea involving Corundum. I've talked about this previously, so if you go hunt down the videos, you can probably find a much more in-depth explanation of most of these things. All right, so moving on to the status updates. So a couple of things to talk about. The main thing that I've been working on, and that's nearing completion at this point, is the new PTP subsystem that I've been working on. I now have that working in hardware, so I need to do a little bit more work to get it all, merged in. But that is running on top of Corundum right now, and it seems to be doing what it's supposed to do. Then the next step on that is to actually switch the timestamp formats to get some savings in logic resources, but that'll be the next step. I've also been doing a little bit of design consolidation, basically where we have multiple boards that are very, very similar and merging them into a single design. So at least for the Alveo U200, U250, and VC1525, all that, I merged that into a single design. I'm not sure if there's much other stuff I might be able to apply the same treatment to, but I'll talk about that in a couple of slides. And I've also been working on some port splitting related stuff and got some ideas on the architectural changes, including the application section pass-through, which I think MLE just opened up a pull request on like an hour ago, so we can take a look at that. And then the potential shared development testbed that I'm starting to put together. That's still going to require a little bit of work to get that operational. All right. So the new PTP subsystem that I've been working on, I've talked about this over the past couple of meetings, so I'm not going to go too much into the weeds in terms of the details here. But the idea is to distribute time from the PTP hardware clock via a single wire that carries a serial format that carries data in a serial format plus the PTP reference clock. So we can get this, so we can transfer PTP time anywhere on the device without causing a lot of routing congestion or whatever. We just have one wire instead of like 96. That makes things a lot easier to deal with. And then we'll have this one wire protocol to transfer the information, and then we'll have leaf clocks instead of the PTP CDC module to transfer the clock into the target clock domain. And the idea is that we'll be able to do this not only with the the 96-bit time of day timestamps, but we'll also use the relative timestamps, the 64-bit timestamps. And if we use the 64-bit timestamps or even a truncated version of that, then that's going to reduce the amount of logic resources that are handling the timestamps. The FIFO bits and blockgram bits and whatnot that are handling these, which should reduce the overall footprint of the design a fair amount. And then from those timestamps, we should be able to reconstruct the full time of day ones for, if the user logic needs to do something or if that needs to be passed back over to the host. So at this point, I have the protocol mostly figured out. I still might make a few modifications to it. We'll see. I have simulation models of the hardware clock and the leaf clocks working in CocoaTV. And I also have the HDL working in simulation and in hardware. I've integrated that into Corundum and done some testing on that. That seems to work pretty well. There's a few other odds and ends I need to do to complete the integration process, basically. But hopefully within the next day or two, that will be uploaded in the development repo for people to take a look at and start using. Like I said, what I have not yet done is actually converted the design to using the truncated timestamps. For the moment, everything just uses the 96-bit time of day timestamps. And I guess another component of that as well is I don't have a module that does the timestamp reconstruction yet, where you give it a truncated relative timestamp and it produces the corresponding full 96-bit timestamp. But that should be a pretty straightforward thing to put together. So hopefully I'll be able to get that operational pretty soon, and we'll get a nice savings in logic resources. Another thing I should mention is that with the testing that I've been doing, with the stuff that I built in Vado using these new modules, the logic resource consumption is about the same as the previous one. So it didn't get a lot bigger. It also didn't get a lot smaller, but the idea is we're going to get the savings when we switch to using the truncated timestamps. I guess I should also mention is that it's about the same size, but it's doing double duty because it's producing both the 96-bit and the 64-bit relative timestamps. So considering we're getting that for about the same amount of logic resources, that's decent progress. All right, so a little bit, I'll go through a few more details of how some of the components work, just in case people are interested. So the protocol that's used for transferring the time, it's basically a 16-bit UART-like protocol, but no stop bits, just one start bit. And the bit clock is the reference clock frequency, so it's basically like a synchronous UART. And one of the nice things about this is you get 17 clock cycles if you deserialize it first to cross that parallel data into a different clock domain. So that makes it relatively easy to put these leaf clocks together. You don't need to jump through a bunch of extra hoops to transfer this relatively high speed serial data into the target clock domain, even if that target clock domain could be slower than the source clock domain. It operates with a 256 cycle update period. So basically, we have a message that gets sent every 256 cycles. And in 256 cycles, we can fit 14 16-bit words and then have one full word of idles at the end for the frame sync to work correctly. If you don't have a full word at the end, then you can run into a problem where it'll never actually achieve frame sync. Now, the format of what's actually in the messages is kind of similar to the GPS almanac, where part of the message is fixed and it's always the same, and then another part kind of cycles through different pieces of information. So the idea is that every frame or every message has all of the information to set the 64-bit relative timestamp clock, and then the portion that cycles out has all of the information for timestamp reconstruction and for setting the 96-bit clock. So you'll set coming out of a reset, you'd set the 64-bit clock, relatively quickly, but it would take, looking at a few more messages before you would be able to set the 96-bit clock or handle timestamp reconstruction. So for the timestamp reconstruction, the idea is we're going to have basically current and alternate timestamps for that define a 500 millisecond reconstruction window, basically. So the idea is the current one gives you the offset for the current second, and you would send the alternate timestamp for the previous second near in the first half of the current second, which would give you, basically 1 second in the past that you can reconstruct over. And then once you cross the center, then once you go 500 milliseconds into the current second, then you would flip to sending the alternate the next second as the alternate offset. So this will give you guaranteed at least 500 milliseconds in either direction across both of the transitions. So the PTP hardware clock is set up to generate these, and then the idea is that you could have a module which receives the serial data and can extract these offsets and reconstruct the timestamps. All right. So another thing that I was taking a look at while I was putting this stuff together is the actual API on the PTP hardware clock that's used for actually controlling the time. So if we're going to be kind of tying the 64-bit and the 96-bit clocks together, the simplest way to do that is to use basically an integer nanosecond offset. So that means that they have to use the same fractional nanosecond field. And the old PTP clock has separate fractional nanoseconds for each of the clocks, which is, well, that wasn't necessarily the best design decision, but changing things around such that they use the same fractional nanosecond field does, it doesn't really add too much complexity, but it did take a bit of head scratching to make it work. But that is a necessary change for that. But that does also require some changes to how the timestamp loading takes place, because on the old clock, you basically just say, here's the current time, and you give it the whole 96-bit timestamp, including the fractional nanosecond portion, and it'll latch it in. But if that field is shared, then it doesn't really make sense to do that. It makes sense to kind of rethink what that interface looks like. So what I realized that there's kind of three different use cases for adjusting the clock. The first thing that you need to do is kind of a course set, where you just set the clock approximately to the right time. But the thing is, the latency between when you issue the operation to set the clock and when the clock actually gets set is unpredictable. So by definition, pretty much just setting the clock outright is a non-precision operation. So there's no point in setting the fractional nanosecond field at all, because it's going to be many nanoseconds worth of latency minimum in terms of when this actually gets applied. So that's so that in some sense makes things a little bit simpler, because for the set operation, well, we just ignore the fractional nanoseconds field, and that works. The second use case is we need to be able to make fine adjustments of the period to slew the clock. And this is kind of by default how PTP works, where the time servo looks at the output of the clock based on the captured timestamps and figures out whether it's running fast or slow, and then adjusts the rate that the clock is running at by changing the period register. This works when the clocks are asynchronous, but in the case of White Rabbit, where everything is synchronous, you cannot touch the period register. So instead, you have to be able to apply offsets to the clock to get it locked properly. So we need to be able to apply offsets to basically all of the different fields. I mean, applying to the relative timestamp, I guess, is not particularly important, but you have to be able to offset the fractional nanosecond field as well as the time of day clock. And then also, while looking at this, I figured it might be a good idea to add some provisions for PTM support, because PTM involves reading basically a system timer from the host. So PTM will synchronize that to the card. But then if you want to synchronize the host clock, basically you need a way to read the PTM time as well as the NIC clock time at the same time. So you can actually figure out which one's faster or slower and do the appropriate steps for synchronization. So by adding provisions for PTM, I'm literally just saying I'm leaving a hole in the register space here where we can put the PTM system timer. Right. So with these observations, this is what the current API looks like for the new clock setup. And this is somewhat similar to the old one, but there are a few changes. So for reading the clock, we have a set of registers where you can read the current time of everything. And it's hard to read stuff consistently from these registers, but there's no, read side effects or anything else, so you can just read it. So if you just kind of need to know what the current seconds field is, you can just use the current time registers for that. If you need to get a precise snapshot of the current time, then there's a set of snapshot registers. And the idea is that when you read the fractional nanosecond register, which is first, then it latches in all of the register values. And then reading the subsequent registers will, read from that snapshot. So you can get, basically a simultaneous capture of, both timestamps plus the fractional nanosecond field plus the PTM timer, once that's connected for designs that support PTM. And then we have set period. That's the same as the old clock. Then we have offset fractional nanosecond. So with that one, you can provide a 32-bit signed number, which gets added to the fractional nanosecond field. So this one will allow you to offset the clock by less than a nanosecond. And then we have set and offset for both of the timestamp formats. So the set TOD timestamp, you provide the seconds and the nanoseconds for the time of day. Set relative timestamp, we provide the 48-bit nanosecond field. Offset TOD timestamp, you provide a 30-bit signed nanosecond field, which will basically give you plus or minus half a second, which will then be applied atomically. So you don't know exactly when it's going to be applied, but because it's an offset, it doesn't really matter. Versus a set operation, which is, again, you don't know when it's going to be applied, but since it's an absolute time, that doesn't work so well for time synchronization. And then and then you also have the offset relative timestamp for if you need to align the relative timestamps for some reason, like if you have multiple FPGAs in the system and they need to exchange relative timestamps instead of absolute ones, then you can offset the relative timestamps to bring stuff into alignment. So that's what the API is looking like at the moment for the new hardware clock, and I have this I have the registers updated, documentation updated, and both the user space tools and the driver updated to use this new setup. Now a couple more details if anyone's interested on the actual modules that I have here. So there's the hardware clock module and the leaf clock module. So the hardware clock module, it's based on a state machine. So previously, the hardware clock module, it basically has to compute a new timestamp on every single clock cycle. So I had to jump through a few hoops and pre-compute a few things, took up quite a few registers and whatnot to do that, a bunch of adders and whatnot. Because, if you got to produce new value on every clock cycle, you can't really stop and, and compute stuff. But with the message-based setup, we don't need a new set of values every cycle. We only need a new set of values every 256 cycles. So in the hardware clock, we now use a state machine to compute the new values by jumping 256 cycles every 256 cycles. So it's great. You can just bit shift the period value and then add it, and everything works. And the fun thing about using a state machine is it means we can do everything with one adder. So there's one shared 48-bit adder that's used for all the operations. And as a result, I'm not going to say the footprint is smaller, but it's than the previous one, but it's relatively small. So we have to handle the drift computation for every cycle, obviously, because of how the drift part works. And then I also have simplified pulse per second output logic, which that has to run on every cycle as well, such that the PPS signal actually fires at the appropriate cycle as opposed to only every 256 cycles. So for this, what I was able to do is use the shared adder to do some of the work. And then we also don't need the full fractional nanosecond accumulator because we're going to be reloading that every 256 cycles. So it will accumulate a little bit of offset, a little bit of error, but that's not really a problem because it's just going to get reloaded and that offset will go away. So that all works pretty well. And we also have better handling of the time of day clock offsets, because previously I didn't have any provisions for decrementing the seconds field, basically, if you applied a big negative offset. But that's now fixed with this new setup. If you apply negative offset, it will decrement the seconds field if needed. Since we're using the 48-bit shared adder, you can take the more direct approach and go, okay, well, if we're beyond if we're beyond plus a billion, okay, then we will subtract a billion and increment the seconds. If we have a large negative offset, then we can do the opposite in the other direction, and it works fine. So that's this is all implemented. It seems to be working pretty well at this point. And then we also have the leaf clock as well, and this one. This is a combination of a couple different parts. Basically, we have a little reference clock in the PTP clock domain, and then a full PTP clock in the destination clock domain. And then there's a couple of PID loops that are involved in, deskewing and synchronizing. So the deserialization logic that's receiving these messages, it generates a delay compensated sync pulse. And the delay in this case I'm talking about is if you have to add pipeline delay in the routing for the serial data, then that can be compensated for because there's just a little counter at the end. So you can, offset that by however many cycles. So that generates the delay compensated sync pulse. And then we have a digital PLL, which transfers that sync pulse through to the destination clock domain. It's not perfect because obviously they're running at different frequencies, but that enables the two clocks to be, or the timestamps to be sampled at as close to the same time as you're going to be able to get. And then we have a time servo PID loop that takes those, sampled timestamps, which should be sampled at the same time, and compares them, and as a result adjusts the period on the PTP clock in the output clock domain. So to do that, we use two different phase detectors. We have a coarse phase detector that looks at bit 8 of the timestamp, and it uses that to get a rough frequency and phase lock on the output. And then once we're close, then we switch to using, we look at the lower 9 bits plus 4 bits of the fractional nanosecond. We subtract that, and that gets you basically a phase offset, which we could then use for the fine phase locking. And then I also used something that I subsequently figured out, I think at least it's called gain scheduling, to improve the dynamics. Basically, I'll change the P and I constants, the P and I gains based on the error. So if the error is large, we use large gains to try and get rid of that error quickly. If the error is small, then we use smaller gains for, better long-term stability and tracking. And so this gives you the lower 9 bits plus the fractional nanosecond bits. For the MSBs, that's just checked periodically. And if they're different for a few cycles, then those get loaded. And then we derive the time of day timestamp from the relative timestamp with a little bit of additional logic. Because we're only dealing with the lower 9 bits, we can just add the offset for those lower 9 bits. And then we just have basically a counter for the rest of it. So that allows you to basically get double duty out of the leaf clock, because we can get both the 64-bit and the 96-bit timestamps wherever you need them in the design. So that about rounds it out for the new time distribution subsystem. Again, I have it working in the hardware. I need to do a little bit of additional work to get that cleaned up and into the Ethernet repository, and then pull that back into Corundum and get all of the designs updated there to use the new modules. So I have that work partially done, but hopefully in the next couple of days I'll have it all finished off. Right, and then the other thing I've been doing some work on is design consolidation. Basically, reduce the amount of code, the amount of designs in the repository by merging stuff that can be done through configuration and through swapping out things like placement constraints files and whatnot. So the main thing that I've done so far is to merge the Alveo U200, U250, and VCU 1525 designs, because the boards are effectively identical. The constraints files are identical. The things are using all the same pins. Previously, the way I was generating the GT cores, you had to have different scripts for, or I guess it wasn't the GT cores, it was the CMAX. You had to have like a different TCL script for each core, for each, or at least for the U250 versus U200, you need different scripts. But that, I have a different way of doing that now, and it only relates to the placement constraints, really. The other wild card is the CMS IP core that is in the U200 and U250, but not in the 1525. So basically, all I need to do is add another board level config option for the CMS IP core, and then I can merge these two designs. Obviously, you have to also pick the correct placement constraints because of the different SLR configuration on the U250. But with that, we can support all of these boards with the same set of HDL files. So that's done. I've been thinking about what other boards might also be able to be merged, for similar reasons. It's possible, I think one of the, like the Exynic X10 and X25 maybe could be merged. I'll have to take another look at that one, because those are pretty similar. I'm also thinking in terms of some of the newer boards, like the U55 and the C1100. Those could be very similar to like the U50 and the U280, similar enough to where they can be built from the same code base. So it's possible maybe even all 4 of these could be built from the same code base. I was just thinking about this a little bit yesterday, so I'm going to take more detailed look at that, and that could make things a lot easier to deal with, because if these things can be built from the same code base, that'll also make it a lot easier to maintain, because you only need to you build it and test it once, basically, because the other board has different pin constraints maybe, but if all the interfaces and whatnot are the same and all the core HDL is the same, then you don't necessarily have to jump through a bunch of hoops to test it on both. The other thing that I've been thinking about doing is merging all of the 25G and 100G designs. And that'll basically mean that every board in the repo will only have one design for it, which I think would be rather convenient. And basically what I need to do for this is have more flexible GT and MAC wrappers. And the idea is that we're going to do that anyway for the port splitting and whatnot. But if we do it properly, then we should be able to configure the wrapper to say, okay, I don't want the 100 gig MAC, I just want the 25 gig ports. And then we can, set up the data path appropriately and whatnot for this to work. And if all that works properly, then we should be able to just have a single unified design. You can build it for 100 gig, you can build it for 25 gig, 100 gig port split, whatever. And everything is done through config.tcl. So that could be a pretty cool setup. I'm going to chip away at that over the next few weeks, hopefully, and we'll see where that goes. Another thing that I've been looking at, kind of related to that, is port splitting. So if we're going to take a 100 gig port and split it into 4 25 gig ports or slower ports or whatever, there's some clocking issues that have to be sorted out. So I mentioned previously the CMAC, well, the CMAC RX side was running in the TX clock domain, but it does support running that with the RX recovered clock, so I went ahead and flipped that, and that looks good. The reason I wanted to flip that is because when you're running with everything, with all the ports split out, the 25 gig RX side, that's going to be done in the recovered clock. So if both the CMAC and the 25 gig max have the same clocking configuration, and that's going to simplify stuff. So I tried that out, and that works fine. So I went ahead and updated all the designs to use the RX recovered clock. I also tested it using separate GTY RX clocks. So basically each receive channel uses its own clock. That works, but I'm holding off actually switching the design over to using that, because it does use a bunch of additional clock buffers. So it's like, well, if you're just running a 100 gig design, you don't need it. If you're running without port splitting, you don't necessarily need it. It's only really necessary if you have port splitting enabled. So I think what I'm going to do is hold off on implementing that until we're putting together a design that's actually going to support port splitting, at which point I'll have to do some tweaking of the parameterization and whatnot, such that we can use the correct clocking structure depending on whether split ports are enabled or not. So on the TX side, I haven't done any work there, but I think we're going to have to add some sort of phase compensation FIFOs, basically, to transfer between the output of the CMAC and the inputs of the GT channels, because the CMAC expects everything to be running in the same clock domain, but if you want to run the 4 channels separately, then they have to have their own separate clocks. And like I said, the buff GT only has one input, so that I don't think there's a way to switch between all of the channels synchronous to the first one and all of the channels running separately. I don't know. If somebody is more familiar with these things and knows of a way to actually make that switch work, that would be cool. But it seems like we might have to add some phase compensation FIFOs, which I don't think is really a big deal. Just be a couple extra cycles of latency and a handful of distributed RAM to make that work. Yeah, so that's the main thing on port splitting. Oh, and then streaming interfaces. I guess I discussed this briefly previously. Another potential issue with port splitting is how do you present the interface to Corundum, and not just Corundum itself, but also the application section. So 4 different options that I thought of. There might be some other ones. We could do a single streaming interface. We could do concatenated interface. We could do single 100G interface plus 25G interfaces, and then we could also do a channel interfaces where you have, channel 0, which is 100 gig, or the first lane of 25 gig plus 3 more 25 gig channels. So I'm not sure necessarily what makes the most sense. I think all of these options have various advantages and disadvantages. And another thing that might be worth considering is maybe doing some kind of a hybrid, like we take one option, like maybe option 3, for example, for the asynchronous interfaces, but maybe we do option 4 or option 1 for the synchronous interfaces. Not sure. And then also a few other things to figure out, like frame preemption. Obviously, if you can do that with a single streaming interface, that's going to make things a lot simpler, but working out, potential head-align blocking problems, that does complicate things. So not sure exactly what that might look like at this point, but I also don't have a Mac, an open source Mac that does frame preemption yet. So it might be a while before that's actually a concrete consideration. All right, so moving on. There's a few architectural changes that I've been thinking about doing. Talked about this previously, so I'm going to just gloss over these things and get to the new stuff. So the single hardware interface, switch integration, application section pass-through. So this is probably, I should definitely get around to talking to this today, because the folks from MLE are on here, and they just opened up a pull request on this just a little while ago. So the idea here is to provide a way to pass a bunch of additional signals, user-defined signals, from the top level of the design all the way down into the application section for, more customized setups where you're going to want to have a, additional signals to get passed in for whatever reason. So with this one, we were looking at how to use macros for this. I think if we end up moving the whole design over to system Verilog, then that's going to simplify it. But if we're working with Verilog for the time being, macros are probably going to be the way to go. So I think a couple of meetings ago we went over this in a little bit more detail, but MLE just opened a pull request on this. I don't know if the folks from MLE want to elaborate on what they've done at all, or
Yeah, sure. Can you hear me actually?
Yeah, I can hear you.
Okay, great. Hi, it's me again. It's Olka. So yeah, if you're looking at the pull request, first things first, it's honestly more of a proof of concept implementation. So this is not like what we would actually want to merge into the master once it's done. This is only for you to look at, like have another example, which is in the Corundum code base. Oh yeah, if you can pull it up, maybe that makes sense.
Yeah. I will do that really quick here. Let's see. GitHub is being annoying. Okay, I want to go to that. Okay. One moment. Let me switch over to that one. That look reasonable?
Yes.
Okay.
That looks good.
Right. Okay.
So yeah, there's like a little description. I mean, we can look at that with like more time. But just to give you an overview, so what I did was I just implemented some kind of proof of concept for the ZCO 102. Now, maybe one thing to note is that instead of modifying the files in place where it's necessary, I decided to, for now, just create a new like kind of app. So to have everything in one place, that it has to be changed, even though it might not make sense from a perspective of how everything is organized here. Because like I said, like for now, it's just supposed to be a demo. And I felt like if it's part of something like a demo app, it should all reside in one directory. So yeah, what I basically, what has been done is like create a copy of the template application, and copy all the files that are part of the infrastructure and the whole Corundum code base there that have to be modified for this kind of example. And then yeah, this is like the commit where everything is modified to have these macros in them. And there's the one file here also that is being added, which contains the macro definitions. And like we discussed last time, I now moved the, oh, that doesn't look nice in the div. But yeah, that
window was too small. Okay.
But like we discussed last time, it's now using like one simple macro definition. So if this kind of macro magic with having nested macros to only type the list of ports once doesn't work with your tool, you can just modify it to type out all the port lists and port mappings explicitly. But you can also use this kind of style. And since this is working with Vivado, I used it here as well. And for the demo, I basically just decided to take the Xelite control slave port of the application block and just routed it back out of the application block all the way up to the FPGA top level. And in there, I instantiated a very simple register that is able to control the LEDs of the board. And I verified that this is working. So it seems to be working as we intend. And if you feel like this code here, from the way it has been done, works for you, then the next step would be to actually implement this properly into the, well, normal Corundum code base and not as some kind of separate demo app.
Right. Okay. Yeah, I mean, it's looking pretty good. I guess you're saying that this VH file always needs to be present because of how this is set up. So we don't, I guess you could potentially add another define to turn this off that you then have to add a -D or something top level define to turn it on.
Yeah, that's a
you
good,
wouldn't necessarily need that.
That's a good point, actually.
I mean, this is looking pretty reasonable to me, honestly. Yeah. Yeah, I definitely like doing it this way, so we're going to have the most flexibility in terms of tools, because if some tools don't like this, like you said, macro magic, then there is a fallback option. So yeah.
Yeah,
okay.
exactly. Yeah, maybe that's actually one more thing to discuss. Like you said, right now there would have to be a file provided all the time that contains the macro definitions, or not contain any definitions at all, which should also work, but you still need the file the way it's done now.
Just something to satisfy this this include thing.
Exactly. Now the question is,
even if it doesn't do
anything.
Right.
That's right. Exactly. Now the question is, do we want to add a toggle for that, like you just said, or I mean, if the whole code is going to be rewritten to be able to instantiate these custom ports, maybe it could also always contain a template file for this.
Yeah,
so
I
if
mean,
there's
that's
some
possible. I mean, it's like right now, the way the application section is set up is we have a top level parameter that basically turns that section on or off, right? So if the application section is turned off, then still having to have this, custom interface file doesn't really make a lot of sense. But I guess the flip side, I don't know if there's really a better way of handling that.
But I guess maybe it's a good idea to actually wrap all these sections that we add with a if app enabled thing.
Well, right. So the problem is the app enable is it's a parameter. It's not a macro, right? And kind of the order of, the hierarchy there is the macros are kind of evaluated first and then the parameters. So you can't really do a macro based on a parameter, but you could do it the other way around. I mean, I'm almost wondering if maybe it would make sense to convert the application section enable into a macro instead of a parameter, right? And if you make that a macro, then it can also apply to this stuff. So if the application section is enabled, then I mean, I guess then you could easily have, two macros, one for the application section enable, one for the custom interface thing. Yeah. Well, I guess I guess maybe you could also
still relies on
now and then have a define just for doing the custom interface stuff. So if you're using the application section, but you don't need the custom interface, then it'll work by default. If you do need the custom interface, then you have to set that macro. And I think there's ways to set top level macros in Vivado. So I think we could even just add a line to the config.tcl, just kind of how it sets the top level parameters. You could also set top level macros. And I think there's ways to do that in other parts of the build system as well. That might be something to look into, because it would be nice to not have to have this this file hanging around just for these macros to work. But if we can add a define around that, and then have a way to set that I
but
think would
Oscar, I guess we had this experiment with on EDA tools.org, I don't know, and in the end it turns out that the tools handle macro expansion differently, right? So some look into the inner portion first and the others in the outer portion. So might this also affect this one? So doesn't we rely then on the
if you put the
if def
include in an if def
requires,
then
yeah. So
I think that shouldn't be an issue. Like honestly, that's
okay.
Well, it'd be
I think that
thing to
should be
test.
well defined.
It'd be a simple
we
thing
need
to
to
test and to see if it works. Yeah,
true.
because you could just add a define and then if def around the include, and if that works, then you can move that define elsewhere. So yeah,
Yes.
so I think we should try that, see if it works. I mean, if it doesn't work, it doesn't work. But if it does work, then that could be a good method for doing this.
So basically, we would just
VH file when
you
you're
would
using
just
the interface.
Sorry. So
Yeah,
we
go
would
ahead.
just extend our EDA playground example with the ifdef and see if it's pretty well supported by the various platforms, and then add this into this approach.
Yeah, that sounds reasonable to me.
Yeah, okay. I guess that's
Yeah,
not a big thing,
So
Oscar,
I
right?
think the main thing that's going to be somewhat tool dependent is how you define one of these, top level defines. Is it like a command line parameter? Does it go into a particular config file or whatever? So we'll see about that.
Yeah, that's right. So I guess for Vivado you can do both approaches. I think you can do this via article command as well as using a command line parameter, I think.
Right. So with the tickle stuff, we can just stick that directly in the config.tickle, and then that'll work.
Yeah.
So that sets all the top level module parameters and stuff too. So okay, one more thing. I've even added stuff in there to change the some of the synthesis place and route settings on some of the slower parts. They need some help. So I put stuff like that in config.tickle as well. It's like, yeah, anything to change project settings, might as well put it in there. So yeah, that I think would be a pretty clean setup, and then we'd only need the custom interface header file where you're using the custom interface. So yeah,
it
nice
sounds
work.
reasonable.
Nice work. It'll be nice to have this this capability. Yeah,
all right.
so I think
great.
This is probably the main commit to look at, just to see kind of what needs to go where. So we've got the port maps at the top level of the modules, or at the instance creation level. You've got the port declarations at the top of the module, and then I think you also have a wire declaration somewhere as well, right?
Yeah, this is optional. This is just for convenience. At the top level where you use the actual wires coming out of the abstraction.
Yeah, there we go. There's a wire declaration. Right. Yeah. So I guess you'd only need that at the top, because everywhere else it's just right. You just have the port declaration and then the port connections. Right. And then you also have the parameters. Okay.
Yeah, that's right.
Nice. I'm just thinking, I guess you still need the if def, because if it's not defined, then that'll be some sort of an error, right?
Yeah, that's right.
Okay.
I mean, we could. Yeah. I mean, if we allow users to completely disable it, no, that doesn't make sense. Oh no, okay, never mind. Never mind what I just said.
Yeah, it's fine. I think we all came to the same conclusion at the same time, pretty much. So yeah, okay. Yeah, that looks pretty reasonable. So I think if we change that up with the include, and if that looks good, then we're probably just about ready to modify all the code and get that pulled in. So yeah, that'd
All
be
right,
very cool.
so
And I guess for that we probably don't need to modify all of the individual designs. Well, or maybe we do. I guess probably not, because you would need to use that on the individual. It's not as yeah, because in order to use this, you have to actually modify the FPGA.v, FPGA core.v for an individual target board. So I don't necessarily think. I guess we'll have to think about that. Obviously, it
yeah,
has
that's
to go
actually
in all
another
the
good
core
point.
modules, but yeah, so that's also a question of, if we're going to make an example for this, we may need to make a copy of some of those files anyway, so we can add the code to the top level file.
But in case we are successful with this if-def method, shouldn't it be then possible to just leave all these instances alone as they are right now?
Well,
Because
yeah,
by default, it's turned off.
well, right, yeah, that's what I mean. It's like, in terms of if we're going to apply this to all the code currently in the repository, well, what files do we need to modify? Obviously, you got to modify, all of the core files, but for each individual target board, do we have to make any modifications to all of those files? From my point of view, it seems like we shouldn't have to make any modifications there at all, because by default, this should be disabled, right? And we don't need to do anything if it's disabled. And if you use it, well, the whole point is that you're going to be making modifications to those top level files to add whatever code you're trying to connect. So
yes,
what we might need to think about doing is adding a target to one of the boards for that does this, basically. I guess we'll
as
have
an
to think
example.
about where that might live, how the example would work. But I don't think we'd have to modify all of the individual boards, so which definitely makes it a little bit easier to add this support, because you're just touching a handful of core files, which is not too bad.
So we could share the example that we just built and toggle an LED on a ZCU102 board as a reference implementation.
Right, yeah. Yeah, so I'm just trying to think about where that example would live in the repository. Would that be like would that live in the ZC102 folder, or would that live in the applications folder? I'm thinking it would probably have to go in the ZC102 folder, but well, we'll have to think about
Yeah,
that.
I think that makes sense, because like the way it's done now, it's actually not completely correct, because right now it lives in the app folder, but it only works for the ZCU102. So I should change that.
Right. Well, I mean, you just put it together as an example that we can look at, but that, that's fine. Yeah, I'm just thinking, okay, if we're gonna actually have an example of how to use this thing, where should that live? But yeah, I think that makes sense to put it probably in just one of the targets. Because I think I have a couple of things that actually build with the application template module somewhere. It could be, I can't remember which file it is off the top of my head, but I know I have something that pulls that in. Might be like the alpha data board or something builds the app template. Or maybe I never committed that, but I had a folder sitting around somewhere for testing purposes to make sure it builds properly. I guess now that I have the DMA benchmark design, building the template one is less useful, because I have a bunch of okay, so there's your precedent, right? So if you look at a bunch of the different targets, you'll see that there's the app DMA bench thing, which builds that app for that board. So I guess we can do that for this thing. You might need to add another copy of FPGA.v or something in there as well for this pass through to work. When you build that application, then it will use the separate copy of the or maybe I guess the FPGA core probably. But yeah, if that makes sense. So under the ZC102, you'd have like FPGA custom app interface, right? And then in there, you would have makefile config.tcl and then FPGA core. And then that would replace the main one.
Yeah, sounds good.
I think that's probably the most straightforward approach. All right, well, that's good.
All right, so then I'll check that out tomorrow. The whole thing with the toggling the custom interface, and I'll get back to you.
All right, sounds good. I'm trying to see if there's anything else in this pull request that's worth taking a look at. Something wasn't happy on the CI side, but I guess that can probably be, that's not a big deal. Something failed, well, it's just a test.
Yeah, maybe an interesting question would be, what's our target code base? So should we kind of wait for 2 days until you commit the new restructured way where you
Right, yeah.
yeah.
So I'm gonna try to get that squared away within a few days here and push that up to the main repository, and then we can just build on top of that, because it's definitely due for a an update of the main code base. Probably should have done that a while ago, but yeah. So after I get this integrated, which might take a day or two, I'll do test builds, make sure everything looks good there, and then by the end of the week, I'll have that updated, and then we can rebase on top of that. And that'll make,
Okay.
well, actually, I guess that probably won't change things very much because we're not touching the individual designs, but it does have the consolidated Alveo designs, so that would be less files to modify if we're modifying the individual targets, but it doesn't seem like we are, so maybe it doesn't make much difference. But anyway.
Yeah, okay, so depending on the outcome of the ADA Playground experiment, so if it works well with the ZIF we just go ahead and provide a new PR, because then it's kind of independent. And if this doesn't work out successfully, then we'll wait until we get the new structure in place.
All right.
Because then it's less work, right? So if you consolidate the designs, then we don't have to change as much files as we would have now.
Right. Yeah. Okay.
Okay, cool.
Sounds reasonable.
That's the plan.
And then I guess there's one other thing that I could talk about briefly on the status updates, because I've been thinking about the, oh, come on. There we go. Zoom is being slow. I've been thinking about the shared development testbed setup. So I talked about this a little bit last week, but the idea is to put together a testbed that people can connect to remotely and play around with different FPGA boards, test code and hardware, build stuff in Vivado, whatnot. So I've got like 3 or 4 different computers that I can use as host machines. I've got various NICs and PCIe form factor FPGA boards that can be connected, various pieces of test equipment like the network tester, PCIe protocol analyzer, whatnot, that potentially could be set up in various combinations. I've got 2 of the HTG 9200 boards. I've got an Arista packet switch, and I've got a couple of these Pilatus optical switches. So the idea is to take all that and put it together and make it accessible. But the thing that I have not figured out yet is how to handle things on the software side. Ideally, the way I would like it to work is that somebody that wants to use the system, they can connect to a web interface of some sort and basically create an image to boot to, and then they can boot that on one of the computers, or potentially multiple computers, and then the root partition will be read-write. So if you make any changes, modifications, or whatever, those will be persisted. So if you shut the machine down and log in later, or if you crash the machine or whatever, then you won't lose any configuration changes. And then everybody can have their own set of images, such that if you had a shared machine with a hard disk in it, then you have to worry about what other people might have screwed up when they're using it in terms of the configuration. But if it's all diskless and stateless, and you have your own directory to work in, then all that stuff will be persisted. And then we can share everything over the network via NFS. What I'm trying to figure out is the best way basically to manage all of this. So I think last time there were a couple of suggestions. One of them is to use some of the the DevOps tools that are becoming more more popular these days. Like I think Puppet was one of them, and Ansible might be able to help with automating some of this stuff. I think I found a couple of kind of web front ends for Ansible as well. I think there's Tower, and then there was a like an open source version of that I'm drawing a blank on the name at the moment. So that could potentially be a nice interface. You can log into that and, you know, run stuff to configure the test bed and boot your image or whatever. That could potentially work pretty well. But what I'm still trying to figure out is how the, you know, NFS shares and net booting is going to work on the host end. Because ideally we would have some, at least minimal level of isolation. So it's like usually when you're doing NFS routes, the root is read only. So you don't need to worry about somebody else with root access changing something or accessing somebody else's home directory or whatever. But that's potentially a concern here. I mean, not so much from security, but you know, it'd be nice to make it a little bit hard to snoop on other people's home directories. But it'll also be useful to try to prevent you know, misconfigurations from causing trouble, right? If you can clobber somebody else's root partition with a bad script or something, then that's something that we would like to avoid if at all possible. But I'm not sure how to do that with NFS. I don't know if we have people that are more familiar with, you know, what might need to be done here. That would be great. If there's other systems that might do similar stuff that we can look at, that would be worth looking at, that would be great. I did notice that it seems like there's a couple of sort of diskless, stateless management tools in the HPC space, but I'm not sure necessarily if those are going to be entirely appropriate for what we're trying to do, because it seems like a lot of this stuff is set up for, you know, ephemeral read-only root partition stuff, which is not exactly what we're trying to do here. Or it's set up to where the users don't have sudo access, which, since we're doing hardware development, everybody needs sudo, so that also complicates things. So I don't know. Not sure what the best approach is, but I've definitely been doing some poking around.
Well, maybe 2 cents from our side.
Sure.
So what we use is, or what we often use, and yes, there is some performance impact on it, but not so much. So we use virtualized environments, and we use the QEMU PCIe pass-through feature, so that a PCI Express device is directly hooked into the VM. So this way you could run kind of fully virtualized environments and boot your whatever VM from whatever image, and you don't need to reboot the machine physically. So maybe that helps as well.
Right. Yeah. I mean, it's like if we weren't doing stuff with PCIe devices, I'd be like, yeah, virtual machines, that sounds great. But I don't know. It seems like that's potentially going to open some cans of worms in terms of, you know, if the hypervisor is doing something weird, or I mean, I don't even know if that works properly if you're hot resetting the device and changing the bar configuration and stuff like that.
Well,
right.
That's stuff we do, I guess.
Oh, and it works?
I need to ask Joachim about this, because he
Okay.
does a lot of this stuff. But at least from a non-FPGA world, so we use it now in another testbed, in our network testbed. We use this to do interop testing, and so we don't want to install like tens of OSs per device.
Yeah.
So we have this virtualized, and the network cards, and in this case, it's not an FPGA card, right? It's a network card that's then passed through into the VM directly, and that is working pretty well. Not sure about FPGA cards. So I think we worked on this in another setup, but not sure how that in the end turned out. I think Joachim did used it like 2 weeks ago with an FPGA running Corundum, or a Corundum based design.
Right.
So maybe he has some more insight into this.
Right, because
But
I
that's
guess
what we
the other
use
aspect
regular
is
with
that it
network
would
cards.
probably work relatively well if the configuration on the board is static, right? If you're just doing driver development and you're not playing around with the image that's running on the FPGA. But as soon as you start loading new images on there and you're screwing around at the PCIe link, yeah, I'm not sure how well QEMU would work that way.
It should
mean,
be
it's
okay because on the hypervisor host, this is kind of how is this? It's used by a VFIO driver, and that's
right.
kind of doing nothing. So it should be okay. Not sure actually, but so if you're interested in this, maybe just
Yeah, maybe
ping
that's
Joachim
worth
via
taking a
Zulip.
closer look into instead of trying to do it, completely stateless and whatnot. Maybe it makes sense to have some sort of a hypervisor run on these things. But I guess that's also a good question as to what hypervisor makes sense. Like, I don't think KVM, well, or maybe KVM is fine.
So that's what we use.
There's several
Qemu
different
KVM.
levels of virtualization. So with KVM, you can run any OS in there, right? It doesn't have to be the same kernel as the host.
Exactly, yeah. So we
Okay.
also did run Windows on these
Right.
setups.
Okay.
Which actually was why we started doing this, because especially Windows is very annoying if you have this set up in parallel with the other OSs, because it keeps rewriting the boot procedure, and that's really bad. And the other thing is, if you have those installed locally, you then need an option to somehow operate those boot menus. And yeah, if you're not right sitting in front of the machine, that's also not so nice. Yeah. Yeah, then there is the other thing, that's the FPGA part, right? So everything is fine if as long as you can kind of reprogram the FPGA in band via PCI Express, for example. But if
Right.
this is not possible, then you also need some infrastructure to do this. So we have, we internally choose LabGrid as the tool to work with. And we use this for kind of allocating resources, managing access, because you obviously don't want two people to run something on the same FPGA card. It won't work.
Right.
And we also use this to program the FPGA. So we extended it, for example, to also be able to program Intel FPGAs via JTAG. Running actual hardware servers for the AMD side, because we often want also to connect the software debuggers that hasn't been supported via upstream. So that's kind of our orchestration hardware support layer. Maybe that's interesting for you as well. So if you're
possibly could also be
so
worth looking
maybe
into.
I'll look inside, and maybe me or somebody else of us can provide a little overview of what we do maybe next dev meeting.
Yeah, that could be good. That could be good. Be nice to hear
So
about
if
some possible alternative setups. Yeah, if this setup is working for you guys, maybe it's worth looking at using that here as well.
So we could definitely share how we do this for now.
So
And
I
we
guess
use this,
another question real quick.
especially we
Does
use this
LabGrid
for a lot of
manage the
projects.
VMs at all?
We use it partially for it. There is no support yet for VMs. So it's more so the original target of LabGrid was embedded device operation. So more like single board computers, supervision. So the idea behind this was to be able to fully automate like firmware upgrade procedures, and stuff like that. We kind of sidetrack this project, or reuse this project for our needs, but yeah,
Is
as
this an
long
MLE product or is this somebody else's thing that you guys have been using?
no, it's a
Leopard.
public GitHub project, ran, I think, originally developed by a Linux focused embedded
Gotcha.
company,
Okay.
also somewhere in Germany. And yeah, it somehow originates from a couple of people, I think, meeting at FOSDEM some time ago. And they were discussing like how they want to debug embedded devices, or for example, smart TVs, right? So they have those firmware upgrades every now and then, and they need to make sure that all these TVs with their different PCB versions, firmware versions, whatever, get updated in a proper way,
So it's a sort
without
of to
malfunctioning.
facilitate kind of a hardware version of CI, basically. It's like, hey, we want to test this firmware across all of these pieces of hardware and run
Yes,
a set of
yes,
tests. Yeah.
exactly. And so the interesting thing is it allows also for orchestration. So because there is a backend where you kind of acquire a place, it's called, and once a place is acquired, nobody else can acquire it or execute an operation on it.
Right. Until you
So
release it. Yeah.
exactly, until you release it, and you can reserve it. So if it's already required, you can reserve and you get access once it has been released. So this way, you could also orchestrate a combined use of the same testbed by human operators and the CI as well.
Right.
So that's why we started using it kind of in very small setups in the beginning with like one FPGA board, and it's more like the original idea of the project. And now it's somehow, yeah, we yeah, started to scale it into test beds where we have about 10 FPGAs, different platforms and vendors and so on. And that's why we also started to add some extensions. Because originally the FPGA support was more focused on updating the firmware in flashes,
Right.
because that's what you do when you originally do firmware updates, right? But yeah, that's not what we usually do. Most of the time we want to debug and interactively operate the device, for example, via chip scope, GDB on the PS and whatnot. And that hasn't been possible originally. But now it is. So yeah.
Well, I mean, maybe this is something worth putting some more cycles into, because if some of these capabilities would just make sense to integrate into LabGrid directly, then that could make it a lot more usable for, you know, for other devices. I guess another potential aspect of this as well is that if it's meant to handle embedded devices and firmware updates, well, what about just making the host machine the target instead of the FPGA board?
Yes, that's also one of the extensions we kind of do. So we have maybe that goes too deep into, but so we can discuss this now, as you like. So what we do is, so we have our lab workstations are all operable via IPMI. So we kind of have a bridge from LabGrid into IPMI to handle power on, power off, for example. And then we can also use LabGrid to SSH into these devices. And once this is possible, then yeah, what else do you need, right? So you can
Right.
stop the machine, and then SSH into it. Yeah.
Right.
And the
Well, I mean, I
interesting
guess,
thing,
yeah.
and maybe that's one last important thing, it's already integrated into PyTest. So if you kind of want to execute CI jobs based on PyTest, LabGrid already has some taps into this. So
Right.
it's possible to integrate it into the setup and the teardown portions of PyTests. So
Right.
that's
Right.
that's an
Right.
interesting feature, possibly.
Yeah. I guess I was also thinking just now that, okay, if you have, well, I guess what you could do potentially is have LabGrid manage a VM associated with each device. So if you have like 2 FPGAs installed in a computer, you could potentially run one VM for each board to get a PCIe pass through to that socket that the board's plugged into, basically.
Yes, yes, that's our approach.
Okay. Instead of
So we
treating the
kind
whole
of
host. So you run you
exactly.
basically so the hosts are not stateless. They have LabGrid running on there, but then they can pull up whatever VM you want internally.
Well, they are kind of stateless because the LabGrid stuff runs on other nodes which are much smaller and less powerful. But so the host is basically only running the hypervisor stuff. It's a fully featured Linux, but there is nothing run from our perspective on
Okay, so you
them.
don't run LabGrid on the host. You run LabGrid somewhere else, and then it communicates with the host over the network.
You know, well, as we need as we use LabGrid to power these hosts on and off, it's not a good idea to run LabGrid on them. But yes, you could kind of do this as you like. You could run LabGrid on the hypervisor. That's not a limitation. You can do this. It's just that we have like central a place to run this because it's the central thing is shared across multiple projects.
Right.
And then there is per project. Okay, now we're getting into the weeds. So there is this central place, which is the gosh, naming things. The orchestration place. Oscar, do you remember the name? Well, it's kind of the central place.
There's two things that are hard in computer science, right? Cache invalidation, naming things, and off by one errors.
Yes, exactly. Yeah, well, so there is a central place which manages the acquiring and releasing stuff, and being the way to go for the client, which you can run on any node. So there is a LabGrid client, and that connects to the central place, and then it gets the information from the central place where to go for to look for resources of a place that it just acquired. And these resources are run on, or maybe run on a separate node or on the same one. And these separate nodes run so-called exporter. And on this exporter node, this is a service, this LabGrid exporter, and that may then run additional services required, for example, to connect to a board. Let's say you have a board that needs to be powered on and powered off and provides a UART. So the exporter now has a way of identifying, for example, the USB UART connected to the board. And if you now say LabGrid client connect to this UART, it starts I don't know the original tool, but it's a regular Linux tool that provides UART via TCP. And then your local LabGrid client connects to this remote tool via regular Linux tools, user space tools. So that's kind of what the exporter does. And the exporter would also run a Vivado hardware server, for example, if you specified this. And there will be a separate power daemon that now also manages power states of the various places. And if you say like LabGrid client place X power on device, then it would send a command to the respective power daemon. And you as a user don't need to know, okay, is this device powered by I don't know, a wireless socket, a power outlet socket, or is
that should all
this?
be automated. You just want to push the button to turn the device on, or it turns it on automatically, and then if it crashes,
Yes,
you can reboot it. You don't want to hit the
exactly.
button to reboot the wrong thing. They're like, okay, it's
You
on
don't.
this PDU. Oops, I meant to push number 5. I pushed number 6. Uh-oh. Hopefully nothing was plugged into that. Yeah.
Exactly. And like us, as we have in one setup, I don't know, like 5 or 6 or 7 wireless power outlets, you need to remember the exact numbers that you now want to repower.
Yeah, that's a problem. Yeah, I remember.
Exactly.
So we have the sysadmin at UCSD has kind of a similar setup with the serial terminals and PDUs for the servers. I guess this setup kind of predates IPMI by a bit, because it seems like more and more servers have IPMI now, but she doesn't like IPMI very much. She likes her old serial ports and PDU thing. But yeah, it's always a question of, whenever you get a new rack setup, getting the mapping correct between the servers and the PDU plugs and the serial ports and whatnot, such that when you connect to one of the servers through the serial console and you issue the reboot command, that it actually power cycles the correct plug. Because if you do that and the server doesn't reboot, it's like, uh-oh.
Yes.
What did I do?
Yeah, exactly. So that's always critical, right? Because you also don't want to kind of interact with a long-running test that already lasted for days of your colleague and then just reboots his machine, right? That's not nice.
Yeah, that's not very polite, is it?
Yeah, no. And there is one issue still left over, and we try to come around this hopefully soon, and that's shared resources. So that's something LabGrid can't handle yet. And you have something like this, and we have something like this, and it could be power, and because sometimes we just want to spend like a per board power switch. And the other thing is, more importantly, a network switch. So a network switch can be shared by multiple setups and places, but you just want to power it once, right?
Right. And if any of those setups needs it, then you turn it on. If all of those setups aren't using it, then you turn it off. And that
exactly
saves power and also saves eardrums. For some switches anyway.
Yeah. Especially these data center grade switches tend to be very loud because usually they are in a rack and it's shielded and exactly.
Yeah.
So
And then
that's
if you turn it
one
on when
thing
it's on your desk, it's like, oh geez, this thing wants to take off,
Oh yes. Yeah, but anyway, so I guess maybe that's a good idea. I see whether Tobias possibly can make it to the next dev meeting and then present what we do. Otherwise, I'll just collect what we have here within of in-house presentations, let's say, and documentation, and then I can just provide at least one example how we use it.
I created a Corundum testbed channel on the Zulip, so we can put that kind of stuff in there and have discussions or whatever. So yeah.
So
if we can
I
come
write a
with a
message
good
there.
setup for this, then I can set that up here and hopefully make it available for people to use. But definitely, well, yeah, and I guess the other aspect of this as well is that with the setup that I'm having here, I also have the Pilatus optical switches that can be used to interconnect various components. So I guess kind of like a packet switch, those would be shared, but also potentially scripted too. Because I know this is something that Carlos was doing for testing some of the. He's been working on the packet switch design, and for testing that, he has to move the network tester ports around. So the idea is that, well, maybe we could script that by using the optical switch. So you can just change the switch configuration to put the testers on whatever ports you want. But I'm not sure how something like that would dovetail with LabGrid. Maybe it wouldn't, and we just kind of have to manage that separately. Not sure.
Yeah. So what we tend to do is we try to use LabGrid for the basis, for the base stuff, and I guess once we have this extension for shared resources, I guess then we are pretty much fine with it, and we have everything we want to have. But after that, we use the PyTest environments we build on top of this to actually run something on these shared infrastructure and set it up correctly. For example, the switches, right? So what we want to do is, if I do a test running on 3 boards being interconnected across our switch, then it would be great to put them into a shielded network segment. Right. So, and that's kind of a similar thing. And once the test infrastructure has knowledge about the physical topology, it can then create automatically logical topologies. But
right, yeah.
so this logic
so
is
it
still
wouldn't
missing.
just like turn the switch on, but it would also change VLAN settings or something.
Yes, and sometimes you
isolate
need
stuff,
additional
yeah.
settings as well. So at least for some Xilinx-based 100G IP cores, for example, we need, at least for our switch, we need to manually do some things on the ports because the auto negotiation part is not provided by Xilinx per default, right? You need to buy a license for them. So you need to switch off auto negotiation, at least for our switch. And then that's also then automated.
Well, maybe it's time to look into that's something I could add to the project slide is auto negotiation implementation. Because I think, honestly, in principle, it doesn't seem all that complicated. I don't know why Xilinx charges so darn much money for it. But if we do have an implementation of that, then we could also use it for 10G, 25G, and 100G probably. Because it's just like a Manchester encoded signal at 156 or 322 or 312. I can't remember the exact rate, but it's like half of the series rate, something like that. So ostensibly at 10G, it's not too hard to drive and receive. At other rates, it is a little bit more complicated. And I think on 100 gig, it's exactly the same, but it just runs on one of the lanes. So in principle, I don't think it would be all that complicated to implement.
I think at least from the specifications, when putting together specifications for boards, I think lane 0 has always to be connected to lane 0, and then everything else is negotiated. So yeah, auto negotiation should be just present on one lane.
Right.
That's at least my conclusion, even though I haven't looked this up in the IEEE spec.
Right, yeah. I mean, I guess the trick with 100 gig is that it should be able to deal with any kind of weird lane muxing and demuxing and reordering that takes place. But I guess it's a slightly different story between the actual, protocol once it's running and the auto negotiation to get it running. Because
yeah, but at
like
least
that only runs on one lane.
Exactly. And that's the reason why there is this lane 0 has to be lane 0 thing. If you switch off auto negotiation, maybe then it's even possible to run 100G in any configuration. Because then you have this lane identifier thing in the PCS layer.
Yeah. So the deal with 100 gig Ethernet, and this is why I looked into it's like, oh, maybe I could make 100 gig Mac. Never mind. They have 20 virtual lanes internally, and that's to support changing the number of lanes dynamically, basically. So I'm not sure if you're aware, but there's like multiple different flavors of 100 gigs.
Yes.
There's 10 by 10,
10 by
there's
10
4 by
or
25,
something.
2 by 50, 1 by 100. And the idea is that the 20 virtual lanes get interleaved on a bit level and distributed across the lanes. So when you have 4 lanes, each lane carries 5 virtual lanes. But which virtual lanes are on which physical lane, it shouldn't matter on the receive end. It shouldn't matter because it should be able to back everything out and undo all of that jumbling and mixing and whatnot.
Yeah, exactly. I didn't know that it was 20, but I would have guessed 10 because 10 by 10 is an interface I know of. Yeah.
Well, yeah, I mean, 10 is not divisible by 4.
Oh, you're right.
That's the problem.
That makes sense. Yeah,
40G is 4.
Yeah, you're right.
But 100G is 20. But yeah, so I do know that it does work with, you know, any random lane mapping, because on this network tester thing that I have here, I managed to score a QSFP to CFP2 adapter, because all the ports on this thing are CFP2s. So I managed to find one of these things. It only works at 100 gig because it has some weird crisscross lane mapping inside of it.
Oh, okay.
And it mixes up everything. So lane 0, I don't know, it doesn't end up on lane 0 at the other end. It would be great if it did, because then I could actually use it as a 25 gig. But as of right now, I can't use it at 25 gig because I have to like send on lane 0 and receive on lane 3 or something for 25 gig to work. But the network tester, it only lets you pick, you know, which lane to use for both TX and RX. It doesn't have a separate TX and RX selection. It's like, come on, how hard would it be to add something like that? But the
Well,
MFPJ is in here after all.
it really, as you say, that might actually be a problem, because isn't it the case that at least some, for example, if you use Xilinx IP core, you can't do this as well. You cannot just use any TX lane and any RX lane. I think they need to be in
For the
one.
100 gig core? For the CMAC?
I'm not sure with 100 gig. I'm
The
not
CMAC
sure with
doesn't
100
care.
gig.
Well,
But
which
for
cores are we talking
25 or
about?
10,
25 or 10? Well, they're all separate, right? So for 25, it's just one TX lane and one RX lane. So
yeah, but you can distribute those on different lane numbers in a GT.
I mean, you should be able to.
Mm.
What do you mean different lane numbers? Like put TX and RX on different lanes? Or,
Yes.
I mean, the problem there is that they have a single channel module. So depending on how the core is built, yeah, you could wire them to different channel modules. But if the channel is inside the core, then you're placing the channel on the device, and you can't handle the lanes separately. But that's, I think, a slightly different issue. If that makes sense, right? Because the pins that you have determine which GT channel gets used. And you can't place a TX and RX separately in different channels. Even though it seems like you should be able to, right? I mean, I don't think there's much. Yeah, I guess there's loopback stuff that connects them. Okay.
Yeah, there's loopback stuff and possibly, I'm not sure, depending on how much protocol level is already also implemented within the, so depending on the IP cores, obviously, if you don't use raw interfaces, there might be some feedback based on comma words from RX to TX.
I mean, I think everything except
No, there
loopback should be
shouldn't.
handled in the user logic, in the fabric, and not in the transceivers.
Yeah, it could be, yes, obviously. But the question is, if there is some more support in the transceivers, and they obviously want to use it for their IP cores to be more compact. But yeah, I guess you can do everything in Fabric, yes, obviously. And then you can, I think then you can actually really distribute these RX and TX on different channels. Obviously, loopback doesn't work then anymore.
Right. Yeah. Yeah, it's like basically if you pull the the GT channel out of whatever core you're using, I think you should be able to mix and match stuff however you want. Yeah. So for board design reasons, if you gotta switch something around, then yeah, then that should be doable. Yeah, I know there's a lot of boards that do when you have the 100 gig interfaces that will mix up the lanes. I think they usually keep the lanes together, but I might need to double check on that. I know there's a couple of boards in the Corundum repository that have a rather non-trivial mapping between the QSFP lanes and the actual GT channels. But I guess with the new wrappers, it doesn't really matter, because you can just keep everything connected appropriately, and then it'll just mix up which channels it uses. As long as the TX and RX matches, then that'll work. Yeah, I guess that's the problem with this adapter here, is that it does mix up the TX and RX. So if I can find one that doesn't do that, that would be great.
CFP2.
Yeah, this is all CFP2. Now, CFP2 is an interesting standard because CFP2 supports 10 by 10 and 4 by 25, and also 8 by 25. But this tester only works at 4 by 25. So you can't put a 10 by 10 module in there, it won't work. Anyway.
Good.
Is there anything else that people want to discuss?
Well, can I just mention?
Yeah, sure.
I think. Okay, so I am starting trying to do some stuff around the oversample 1000 base X.
Oh, right, doing the oversampling, right.
Yeah, so I have brought up the set CU 102. Yeah, I have started doing some testing with the word. I think I'm going to try to what you told me also to try to maybe migrate the XFCP example to the ZCU to be able to talk to the transceiver to get some information and also perform some tests to start working with it. And the first thing that I have observed is that some of the examples that you have with the are with the GTY.
Yeah.
And this board is DTH, so I think I will have to do some changes around that to or maybe they are almost.
I think they're pretty similar. There might be a couple of minor differences in the clocking network. There's I mean at 10G, I'm trying to remember. There's so basically on the transceivers there's a user clock and a user clock 2. And in some cases they run at the same frequency. In some cases there's a factor 2 difference. Like user clock runs at double the frequency of user clock 2. And so under certain circumstances, it could be on the GTHs at 10G, you might need to have that factor 2 difference in there.
Okay.
And that requires a slightly different clock, because you need 2 different clock buffers for each of those versus on the, if they're running at the same frequency, then you can drive it off the same clock buffer. I think that's really the only major difference between the two. There might be some pin names that are a little different or something, but everything else should be pretty similar.
Okay. So I think I will start with that, trying to migrate it, try to talk to the transceivers in the ZCU.
Yeah.
Yeah.
So I think I might have mentioned previously just kind of what the series of steps would be for testing that out. I think the first thing is to put down 2 transceivers running at 10G, talking to each other, make sure that works, and then put down another pair of transceivers running at basically 1 gigabit per second, right, or 1.25, right, and have those talk to each other. And then the next step would be to take one of the 10G transceivers and implement oversampling logic. And you can start out just on the TX side, for example, and then test that to make sure that works, and then try on in the RX direction. And all this would be done with PRBS data. You wouldn't need the whole MAC and everything attached behind it.
Okay, yeah, with the pattern.
That makes sense. Yeah.
Okay, cool. So yeah, I will keep working on this.
All right, and hopefully
I'll let you know what I can achieve.
Hopefully that works, because if we can get it working and it works reliably, then that I think is going to work really well for White Rabbit stuff, I hope. And then it should be useful just in general for running stuff at lower rates. So
yeah, right.
I think basically once we get the transceivers themselves working, then we'll also have to write a soft gigabit 5, and then potentially some adaptation logic to connect that to the Mac. Because that's the other thing, is like, hey, if we can use the 10 gig Mac at 1 gig, then that'll save having to put down a whole nother Mac and with converter and data path and whatnot. So I think that should be possible. Right. I have also been planning on making some modifications to the Mac and the 10 gig PCS components to basically to support more stuff on the SerDes side. So that I think the main thing that needs to be handled there is we need some modifications to support talking to the synchronous gearboxes. which we're going to need to use that for White Rabbit at some point for more consistent latency. But the idea behind that is we should also be able to use it if we want to run the 10 gig Mac in 1 gig mode, because we're going to be basically clock enabling it to run at a much lower frequency. So
okay, cool.
That's kind of the high level idea, and we may need to make some modifications in terms of capturing the timestamps as well. So we'll see about that. But yeah.
Okay, yeah, I'll let you know, guys, how it goes. And also, just to mention that, yeah, also based on the idea of the open source for TG Mac on PCS, that I have, I'm a student, as I commented to you, a master's student that is going to start his thesis on this. So also
building the open source 40 gig Mac. Okay.
Mac,
yeah, because I know we've had a couple of people asking about, hey, do you support 40 gig? It's like, well, you could absolutely drop one in there, but I don't know of an open source one. So I think some poking around revealed a couple of different potential projects that can be used for ideas. There was one project that I think has kind of the Mac, and then another project that has like part of the PCS or most of the PCS. I think that we posted some links in the Zulip somewhere. If you poke around, I'm sure you can find them.
Okay, yeah, I think I remember, from a previous meeting,
Isn't the actual PCS like almost the same? You just need to kind of reorder the PCS
for 40G
frames,
right? So at 40G, since you have multiple lanes, you need to do things that you don't need to do with normal Ethernet, right? Or with normal
of course
25 gig where you just have one lane. So you need to do on the transmit side, you need to do the symbol distribution across the 4 virtual lanes. And you're gonna have a 1-to-1 mapping with the 4 physical lanes, so that doesn't really make too much difference. And then you have to do alignment marker insertion, where periodically you have to insert the alignment markers, but you have to make room for those somehow. I'm not 100% sure off the top of my head how you make room for those, but
I guess
because obviously you can't replace the actual packet data. So yeah,
but there is idle symbols in there, right?
Well,
and
yeah,
you can,
so I
think you will.
Right. So the thing is, the alignment markers are inserted at with a very specific spacing. So you don't insert them into idles. You insert them at the specific cycle where the alignment marker is required. It's like every 65,535 cycles or something like that. You have to insert.
Yeah, there was a specific number. Yeah, right.
Right. Yeah. So it doesn't matter if it's in the middle of a packet. So if it is in the middle of a packet, well, you have to delay that packet, which means I'm guessing there has to be like an elastic buffer or something to store it and remove idle characters between packets or something. It does kick the can a little bit in terms of how exactly you're going to be making room for that. So that's a little bit non-trivial to get that in there. And then in the receive direction, you have to extract, or you have to get you have to do the deskew, which means on each of the 4 lanes coming in, you have to look for those alignment markers. So you have a FIFO, and you look for the alignment markers coming out of the FIFO. When you see alignment markers in each lane, then you'll stop reading stuff out of the FIFO until you see all 4 of them. And then at that point, you'll be aligned, and then you have to remove the alignment markers, which now means you kind of have to do the inverse of what you did before, where you now have this hole that has to be filled, which could be in the middle of a packet. So again, I think you have to have some sort of elastic buffer or something to remove that gap on the other end. Let's see. And then you might have to reorder the virtual lanes as well, because it's possible that you would get lane 0 on lane 3 or lane 4 instead of lane 0. So the alignment markers on the different lanes are different, so you have to get those back in the correct order. Yeah, and then is that it at that point? Well, right, at that point, then you have your 256-bit wide XLGMI. I can't remember what they call it. It's a 25 gig MII interface, which you then feed into the Mac, which then has to do the FCS computation, but with probably a much wider interface, right? 256 bits, I think. So that's that could take some doing to get that working.
Yeah, that's right. Okay, makes sense.
Thank you for the summary.
The Mac itself is actually not all that different, right? Because, you know, you basically just make it wider. Oh, I guess there is one other difference as well. So with 10 gig, the line coding allows you to start a packet either in lane 0 or in lane 4. But with you know, in each control character, because they're 64 bits wide, right? So you've got 8 bytes. You can either put the start in lane 0, you can put the start in lane 4. For 40 gig and 100 gig, you can only start in lane 0, which simplifies things a little bit,
Right.
because you don't need to shift that back. But because you have your 4 virtual lanes, you can start the packet in any of those virtual lanes. Doesn't have
So
to
in the
start in
end
the
it's
first
worse.
one. It can start in the second, third, fourth. Yeah. So yeah, it simplifies things in one way, but makes things more complicated in another way.
Right.
Yeah. And then you also have to deal with fun stuff where you have a packet end and another packet start in the same clock cycle. So that's also fun.
Yeah. Okay, yeah, I think it will be an interesting project. And
Yeah,
hopefully
so
by Jan or something, that is the end of the deadline. So hopefully we have something
yeah.
working.
Well, so the nice thing about working on the having the master student whatever work on the 40 gig Mac instead of the oversampling thing is that it's not on the critical path to anything. So if they take
Right.
several months, whatever. I
Yeah,
would just like
yeah.
to see something working that's in one of the repositories that we could use in Corundum. You know, that would be great.
Yeah.
But yeah.
Yeah, I try to put also divide my time also in the Switch and also in this oversample version of the 1000 base X to be able to to help with this.
Right, yeah.
So
Yeah, the other thing I should mention, I suppose, about the 1000 base X is that it would be nice to do it in a way that we can do both 1000 base X and 2.5G base X, right? Which is 2.5 times faster.
yeah,
The main there's the main difference between those two is the oversampling ratio. So obviously you need a different gearbox. But if you want to support 2.5G base X, I think it makes sense to build a 16-bit data path PCS instead of an 8-bit. But we might want to do that anyway, because there's something funky about like even and odd symbols. So it might actually be easier to do a 16-bit, because then you have a lane 0 and a lane 1, and your even and odd just kind of work out. And then you can also use that for the 2.5G base X.
You think even an odd symbols 8B 10B?
Well, yeah, so it uses 8B 10B encoding, but from looking at I have not looked into the spec in great detail, but I seem to remember there's something about you know, certain symbols are sent on even cycles and other symbols are sent on odd cycles. Maybe it has to do with the idle characters or something. I can't remember what it is, but it's like it's
from
not,
my
it's not just a
last
single
recall,
stream. It's kind of these interleaved. Yeah.
Yeah, but I think that the reason was different. So I think even an odd refers to the DC balancing. So if there is like
No, it's a different thing. It's a different thing. I
it
know what you're
is.
talking about in terms of the
I think if there was if there is like a +1 in one character, you need
right,
to
there's a running disparity.
use the odd one.
That's something else, because that's handled by 8B 10B.
Yeah, but you have this for the same thing. You have like two codes. You have the even code and the odd code.
Right.
To maintain the disparity.
Right. But so my understanding with the 1000 base X spec is that you have to send the idle characters in a very specific order.
Oh, okay. No, that's
you
something
can't just
different.
start with a particular one. It's depending on the even cycle or odd cycle. Yeah, I need to take another look. It's a vague thing that I seem to remember something along those lines. I'm like, oh, so maybe it'd be easier to do a 16-bit wide thing anyway. Yeah. One thing that interesting to note is I did a bunch of poking around at this, trying to figure out kind of what all the specs are and what all the differences are in terms of stuff that's slower than 10G. Well, I guess also faster than 10G too. I think I talked about this a few meetings ago, but I'll just go over the summary of stuff that that I was looking at. So there's 1000 base X, there's 2.5G base X, there's 5G base R, 10G base R, and 25G base R, right? So the base X, they're all basically the same, and the base R, they're all basically the same, right? It's just the difference in the line rates. So it's like 5G versus 10G versus 25G. The encoding is exactly the same. The only difference is, you know, the line rate you're running the serializers at. So I don't know if anybody uses 5G base R, but I'm like, well, hey, if we wanted to do 5G base R, I think we could just flip the divide by 2 bits of the series and we're there. For 1000 base X and 2.5G base X, interestingly enough, they are defined by different parts of the IEEE spec. So there is apparently a slightly different definition for 2.5G base X, but they have an addendum or footnote or section talking about, well, what happens if you take 1000 base X and run it at 2.5 times the speed? And that actually works. And they've actually made some specific modifications to one protocol or the other such that it's interoperable. So if you have a proper 2.5G base X and a 1000 base X running at 2.5 times the speed, they'll talk to each other and it'll work.
Okay.
And I think it was that section that I was looking at that exposed some of these slightly head scratcher things. So I need to take another look at the spec because this was like several months ago that I looked at that. And yeah, so I think the bottom line, we implement 1000 base X. We basically ignore 2.5G base X because you can run 1000 base X at 2.5 times the speed and it'll be interoperable. But we implement it in such a way that we can run it at 2.5 times the speed and it'll work as expected. So, because I think the oversampling works out such that if you do a 16-bit wide interface and you do 16 into 66, I mean, it might not be quite, I can't remember the exact numbers, but it seemed like it worked out, it might work out pretty well if we have a 16-bit wide interface and we can run everything at the same clock frequency. But it's also, but I also don't know about that oversampling ratio if that would work. So that's like a stretch goal. We'll get it to work 1000 base X on a 10G transceiver, and then okay, if that works, well, hey, can we do 2.5G base X? And does that work?
Right. Yeah, I think it makes sense, and it's also an interesting part to also to try and to
yeah. And then I was thinking, it's like, okay, if that's just a different gearbox module, well, then it's really not all that much additional logic resources to support that, if that really is the only difference. So anyway,
cool. Thank you.
It'll be nice to hear about how that's coming together.
Yeah, hopefully.
I'm sure you'll get a lot more familiar with how these serial protocols work.
Yeah, sure.
How the SerDes blocks work.
Yeah, for sure.
Yeah, and I guess the other thing that might be fun to do too is to try to run that, do that downshift on other devices as well. Like, it's one thing to get it working on Xilinx devices, but hey, does it also work on Intel devices, for example? Can you run that on the Stratix 10? Can you run it on the Agilex devices? Don't know.
Yeah,
that could be interesting. Because that's one of the things. I'm like, hey, if we can do this with the 10G transceiver in its native configuration, then anything that has a 10G transceiver, you can run it at 1 gig.
Could be able, yeah. I know it's a good capability. So interoperability. Nice.
And I guess potentially we could also do something for 5G base R. But it's like the other thing is like, if nobody uses 2.5 and 5G base X and base R, then what's the point? Because I think a lot of the PHY chips that translate to, I think they call it like NG base T, that supports all of the oddball rates over twisted pair. Those I think all use like US XGMII or something, which might be interesting to support as well, because my understanding is US XGMII is basically just XGMII, but they send the same character multiple times. So if you're running at 1G, yeah, you send everything 10 times.
Okay.
That's similar like SGMII, right? Okay, interesting.
Yeah,
so
literally, it's just it's the same idea as SGMII, right? If you take SGMII and you run that at 10 megabits per second, you send each symbol 100 times.
Wow.
And that's how you get the correct rate.
Mhm.
So I think I'm not actually sure if the phi looks at the first symbol or if it looks at some other symbol, down the line in each group. But yeah, that's when you're changing the link rate, you don't actually change the series link rate. So you have to fill in
I see.
the rate difference somehow. And I think the US XGMI, even they have some sort of multi-lane version of it where it can support multiple ports interleaved somehow. Not something I've looked into, but it's like if you can get the little optical transceiver plug-in modules that speak US XGMI on one end and NG-based T on the other end, then you can stick that into any of the FPGA boards and run at those rates. Otherwise, I don't have any boards that even have a US XGMI phi on there or anything, so it's not super interesting to look at in that sense. But anyway, Ulrich, were you
Okay,
going to
cool.
say something? I know you guys were working with QSGMI. Was that it? Like 4
Yeah.
ports on one, but that was being weird, right? You never got that working properly.
Yeah, right. So we had one phi that could actually run this, and in the end, we fell back to running those separately.
Right.
So
I
we
mean, I
use
guess something
SGMI
like that
instead.
probably makes a lot of sense if you have a lot of ports, right? Like a
Yeah, it does.
big
Yeah. So we have a
switch where
12
you
port
have.
phi. So
Oh,
we
you
use a
have 12
12 port
ports.
phi
Okay,
on
I
one
see.
board, and yeah, so we use 10 ports of this one. But anyway, the original
I see.
idea
Okay.
was to save a lot of power by just
Mm-hmm.
using 3 transceivers instead of 10.
Okay.
But
Yeah, I guess that
yeah,
well, I mean that's an interesting question. Running more transceivers at a lower rate versus or more transceivers at a higher rate versus less transceivers or more transceivers at a lower rate, does that make a huge difference in the power consumption? I mean, I guess it depends a lot on what parts you're using. Like I know the UltraScale Plus parts, they can do SGMII over just normal IO pins. So that to 10 phi chips versus QSGMII with probably the GTHs to multi-port phi chips. I'm not sure how that would compare power-wise. I guess sounds like
yeah,
maybe
but
the QSGMII ones use a bit less, but
we definitely wanted to use transceivers anyway because I think we couldn't afford the resources to implement 10 8B 10B interfaces in user logic. So yeah.
okay.
So the question was just, do we need 3? So do we basically need 1 quad or 3 quads? And I
Right.
guess if you power down a quad, that really makes sense. And you will see this in the power utilization.
Right. Well, I know the well, yeah, I guess because you're not running all the PLLs such, so that would definitely save some power. But yeah, I know the power is definitely dependent on the link rate as well. So if you crank up the link rate, I know that definitely cranks up power. So 3 lanes
Yeah.
at 4 gigabits a second or whatever, 4 or 5, I don't know what rate that runs at, versus
5.
what I guess that would be 10 lanes at 1 plus a couple extra PLLs. I don't know. I guess 3 lanes you probably get more power savings for over 10, but it's not like immediately clear like, oh yeah, that would save a lot of power. It's like, well, maybe it would,
Yeah,
but
no.
you have to pull up the
It's not like it
English
halves the
power
power
estimator.
utilization.
Right. Yeah. I just know that when I was taking a look at getting the all of the 25 gig ports operational on these high-tech global boards, I was looking at the power numbers out of Avato. I'm like, I gotta check the converters on these things to make sure they can give us enough current. Because
Oh yes.
those things draw that's a lot of channels, and that draws a lot of current, more than you would expect. And it's also interesting. It seems like most of the current is on like the VTT rail for some reason. I'm like, it seems like it'd be on the VCC int or whatever, but I don't know exactly how the transceivers internally are built. So there's probably a good reason for it, but it's like it doesn't make sense just first pass why it would be like that. Anyway, be looking forward to how the 1000 base X stuff comes along. And if you have any questions,
yes.
feel free to post on Zulip.
Okay, nice. Thank you very much.
So actually, if we have if you have this running, maybe another interesting aspect would actually really to look into SGMI then.
Right. Yeah. So that's a good point. SGMII should be very similar to 1000 base X.
Yeah.
I guess there's kind of two main differences. One of them is that there may need to be some amount of auto negotiation to actually talk to a PHY chip. And then the second one is SGMII supports running at lower rates, not through reconfiguring the transceiver, but through symbol duplication.
Yes.
So I actually need to look into getting some SGMII SFP adapter thingamajiggers, because that would be a good thing to test with. We can whack those things in and run SGMII to that, and then test it at different rates just to make sure that works. Yeah. I guess another thing too is that once we get this thing working with the transceivers, it would be useful to look into making it work with the bit slice logic as well, with the normal I/O, basically to take a look at the Xilinx's wrappers for doing that, and you know, implement something similar. Because at least for some of the White Rabbit stuff, we might need to get a little bit more down in the weeds with what's going on there, versus you know, using the Xilinx core where we might need to modify something or poke at something that's, you know, in the encrypted part, and then it's like, well, okay, never mind.
Yeah. Okay, nice.
Anyway, we got some work to do, but sounds good. Making some progress. So
Yeah.
Carlos, you have got two different students, it sounds like, that might be interested in getting up to speed with some FPGA stuff.
Yeah, the other one, have one in the master thesis with the, we do the 40G Mac, and another guy that will help building the packet generator, the traffic generator, mainly focus on to be able to test the switch implementation. But yeah, a packet generator, yeah. So yeah. And this
Well,
is from
I guess with the packet generator, it makes sense to do probably a packet generator and some sort of a checker, you know.
Yeah, right. Also
because it's one thing to be able to
verification,
generate
yeah.
a big blast of packets,
Yeah,
but
that can
being
be
able to
easy.
look at those packets and go, oh,
Yeah.
we actually received them all, or oh, we were missing like 1 in 1,000 or something.
Yeah.
You know, that
Sure.
would be
Also,
that would be good. I mean, I think the checker is potentially going to be more complicated than the generator, but I don't know.
yeah, probably also checking that the frequency is
But yeah,
right.
so it's like if you're getting a student to work on that, you know, it probably makes sense to you know, kind of flesh it out into its own project.
Yeah.
But yeah. And then I guess well, I guess the other thing you'd have a student do is work on a couple of different variations of it, in different sizes. So like it would be very cool to have one that's really small, but maybe doesn't support very many features. So we can just
like
drop
one type
that
of traffic
into
and only
Corundum, and then we could use that for testing stuff, and it could just be kind of there as a self-test thing. And then you could have a more comprehensive one that you can drop into the application section and, you know, send that out the door.
That could be nice, yeah.
Because that could be a pretty good setup for testing the switch as well. Because like I said, I've got or like a, you know, you saw when I got those FPGA boards, right, that have the ultra scale devices on there. What I've been thinking about doing possibly is getting like a PCIe expansion frame, load it up with those cards, and then well, that would be 32 ports. We could run that to various devices for traffic generation purposes. So, you know, cross connect that with one of the high-tech global boards. That would be pretty
not bad at all, yeah. Yeah.
Yeah, so even though if those boards are not the best boards for running Corundum itself, they're potentially useful for, you know, development purposes for testing other stuff. So
right.
I guess that's another thing I need to look into on those as well. I have not done anything with the 100 gig max on Ultrascale, only on Ultrascale Plus. Ostensibly, the Ultrascale ones also have CMAX. They don't support RSPEC, but they have the CMAX. So at some point, I'll get around to it. Maybe.
Yeah.
Anyway, anything else people want to talk about, or nope?
I think I'm fine.
Sweet. Boy, it's 11 a.m. already. Okay, well, I'm not gonna argue with that. Good discussion. That's the whole point. All right.
Yeah.
Well, and also, Carlos, if it makes sense to loop any of these students into these meetings, I mean, they're welcome to join us if
Okay.
they want to. If they don't want to, I mean, great. You know, whatever makes sense.
Yeah, I let them know. I mean, right at the beginning is like more like, yeah, checking some references to get
Yeah.
yeah into the topic. But yeah, maybe at some point, maybe after 1 or 2 months, maybe it makes sense to try to introduce them to also to this.
Yeah,
Yeah,
possibly.
can be nice.
Yeah, and I
Okay,
guess
thank
we
you.
should also poke Antonio as well and see if
Yep.
he wants to get more involved with stuff, because I know he was doing some testbed related stuff. So he might be interested in some of those discussions.
Yeah, I talked
so-
to him. I think he will try to join some of the meetings also.
Yeah. Okay.
So cool.
All right. Well, I guess if we have nothing else to talk about for this week, then I'll see you guys in 1 week or 2 weeks, depending on whether or not you're interested in the Switch.
1 week, 1 week.
1 week. Yeah, for you anyway.
For everybody.
All right.
Right.
Sounds good.
Okay,
Well,
so thank you very
talk
much.
to you guys later.
See you.
Thanks a lot, guys. Bye bye.
Bye. See you.